टेस्ट हुआ था, उस टेस्ट में काफ़ी प्रॉब्लम्स हो गई थी सर हमें। एक तो सर
क्या हुआ
पहले
था?
आपने एमसीक्यू टेस्ट बोला था सर, उसके बाद वो सब्जेक्टिव हो गया था। उसके बाद वो
दोनों
सर
बोले थे
टेस्ट
मैंने,
आपने,
एमसीक्यू सब्जेक्टिव दोनों बोले थे।
सर वी वर इन्फॉर्म्ड कि सर सिर्फ ऑब्जेक्टिव पेपर
सर
है
ये सेकंड
इसीलिए।
वाला पेपर ऑब्जेक्टिव होगा। और दूसरी बात सर, आप वो 12:15 पे आपने पेपर दिया था और 1:30 पे टाइम था, लेकिन सर सिर्फ सब्जेक्टिव वाले पोर्शन पे टाइम 1 hour 30 minutes लिखा हुआ था। तो सर
जब
जब टाइम
ऑफलाइन
एक्सटेंड भी हुआ
सुनो
तो
सुनो
वो
मेरी
हमें,
बात सुनो सुनो मेरी बात पहले सुनो, जब ऑफलाइन पेपर होगा इससे बहुत टफ पेपर होगा। कहीं नहीं लिखा होगा सब्जेक्टिव ऑब्जेक्टिव है, और बहुत मुश्किल से बहुत टफ पेपर होता है यहाँ पर, है ना?
नहीं
तो
सर
ये
टाइम,
सब बहाने नहीं चलेंगे आपके कि आपको ऑब्जेक्टिव पेपर था, ऑब्जेक्टिव पेपर था, यू शुड बी एबल टू डू ऑल द थिंग्स।
नहीं सर टाइम की प्रॉब्लम थी
टाइम
सर।
की भी
टाइम,
प्रॉब्लम कुछ नहीं थी, बहुत छोटा पेपर था वो। जो पेपर आएगा वो जब 1 घंटे का मिड सेमेस्टर होता है उसमें 5 क्वेश्चन होते हैं, और जो 3 घंटे का एंड सेमेस्टर होता है उसमें 10 क्वेश्चन होते हैं। जब ऑफलाइन पेपर, अभी आपने एक भी पेपर ऑफलाइन नहीं दिया, जब ऑफलाइन पेपर दोगे तब बहुत मुश्किल पेपर होता है ना? तो मेक श्योर कि आपको आदत, तो जैसी यूनिवर्सिटी खुलेगी आपको सबको ऑफलाइन पेपर देने हैं।
नहीं सर
सर
हमें
कब
सर
कब
टाइम,
खुलेगी?
सर टाइम जितना भी होगा वो टाइम मतलब पहले से आप इन्फॉर्म कर दीजिएगा सर, हमें एग्जैक्टली पता नहीं था कितने टाइम का
हमने
पेपर।
मैंने आपको मना थोड़ी किया था सबमिट करने के लिए। 1:30 पे पेपर जब हुआ आपका, 1:30 पे यू आर एबल टू सबमिट पेपर।
नहीं सर वही टाइम 1:30 था, तो सर उसके बाद शायद टाइम एक्सटेंड हो गया था जो हमें पता नहीं था।
भैया
मतलब
आप,
वो बस सर
जिन
1:30
जिन
तक
लोगों ने लेट
वो
सबमिट किया
पता नहीं।
उन्होंने लेट सबमिट किया। मैंने जब पेपर बनाया था तब मैंने टाइम देख के फिक्स किया था कि कितना बड़ा पेपर है और कितना टाइम लगेगा उसमें, है ना? सो दैट इज नॉट ए एक्सक्यूज कि वी आर नॉट एबल टू कंप्लीट द 3 क्वेश्चन इन 1.5 hour और द 1 hour, है ना? यू हैव टू कंप्लीट द पेपर विद इन 1 hours इन द मिड सेमेस्टर। दैट विल बी वेरी डिफिकल्ट।
सर ऑल्सो सर ईएडी के लिए सर स्टडी मटेरियल आप सर थोड़ा प्रोवाइड कर सकते, क्योंकि जितना अभी तक आपने दे रखा है उसके हिसाब से सर काफी मतलब मुश्किल हो रही थी वो लंबे आंसर्स आंसर्स करने के लिए, कि वो प्रॉपर एक मटेरियल नहीं है। तो कोई सब बुक या कोई नोट्स अगर आप दे सकते हैं तो।
Book I have already told you, one book is Bhattacharya book, chemical equipment design, mechanical aspect Bhattacharya, that you can purchase. That book cost is around 200 rupees. Okay, online book you will not find, है ना? Any online book. There is a one code which we will follow when we start the design part, है ना? So in the next class from this this week only, we will start the designing and the numerical part. Okay, so in the numerical part we will follow the SI code. Okay, so that code I have already shared with you, which you have to follow. Okay, so that in that code you have to follow the basically there is no standard book for design. This design course is only related to the mechanical design, so you have to just follow the SI code, and in the SI code whatever the methods is given you have to follow that. Okay, the initial part, the chapter 1 and 2 is related to the introduction of design. What are the different aspects of the chemical engineering part, and what are the different type of equipments used in the chemical engineering, that you will find on internet, है ना? There is no standard book for that also. Okay, for design part, for the numerical part you have one book, chemical equipment design by the BC Bhattacharya.
ओके सर।
So in last class, so today is the transport phenomena class. In last class we have solved one problem related to the tube flow in the screen is visible,
Yes, sir. It's
Yes
totally
sir।
right.
है ना? So in last class we have solved one problem related to the tube flow inside the flow of fluid inside the tube. Okay. Today we will solve another problem, that is falling film on the inclined surface. So this is the simple problem. In this problem, you have an inclined surface, solid surface. At this solid surface, the angle of the surface from the vertical axis is beta. This is the vertical axis. The angle between the solid, the inclined surface and vertical axis is beta. Now, there is a fluid which is freely falling on the solid surface. Okay, so there is a film of fluid which is freely falling on the solid surface, inclined solid surface due to the gravity. Okay, now you have to determine the velocity profile of that fluid which is freely falling on the solid surface. What should be the velocity? What is the velocity profile? What is the volumetric flow rate and velocity profile of this fluid? Okay, so the problem statement is an inclined surface of length L and width W is situated at an angle theta to the vertical direction a Newtonian fluid is freely falling on the surface as a film of thickness delta. A Newtonian fluid is freely falling as a film of thickness delta okay. Assuming the flow to be laminar, determine the velocity profile. So this is the problem. Okay, now you have to determine the velocity profile for this problem. So the procedure will be same. First you have to draw the diagram of the system. So start with the draw the diagram of the system. This is the inclined surface. The angle between the inclined surface and the vertical axis is beta. This is the film, water film or the Newtonian fluid film, which is flowing on the surface due to the gravity. Okay, this
Gravity.
is freely falling means it is flowing due to the gravity. Okay, the thickness of the film is delta. It is given. Okay, now second step, you have to put the coordinate system. So this is the vertical. This is the rectangular film, and the thickness you have the length, width, and the thickness. So you can use the Cartesian coordinate system. Okay, in the Cartesian coordinate system, you have the x, y, z axis. Okay, so you have to put the coordinate system in such a way that the system will become more easy to solve. So in this case, what we will do, we will use the upper axis. upper layer as a origin. Okay, so this initial point, upper point is 0, origin point. This axis is x-axis, this axis is z-axis. Okay, you can take bottom line also, that will also no problem, you will have the similar answer. If you take the upper point, the answer will be more easier, you know, the mathematics will become more easier. That's why I'm taking the upper point. You can take the middle point also, like the tube, that is also okay. You can take the bottom point, that is also okay. Okay, so I am taking the uppermost point 0. This is the z-axis, this is the z-axis, this is the x-axis. Okay, now then you have to take the assumption. Third point is take the assumption. First assumption, the assumption will be more or less same in our problems. Okay, constant density and viscosity for the fluid, so that you can use the, you can simplify the problem. Constant density and viscosity. It is a Newtonian liquid. Second assumption is steady state. That means every property is constant with time. The third point is laminar flow. Laminar flow is applicable because in turbulent flow, the velocity, local velocities may depend upon all direction, and that will also the unsteady state condition. So we will assume, we will solve the problem for most simple form in the laminar flow. The fourth point is fully developed flow. The fifth point is Newton's law of viscosity is applicable. So these are the 5 assumptions which we will use. One more assumption you can use, that is the no slip boundary condition, that is used for solving the problem. No slip boundary condition is applicable. Okay, once you written the assumption, you have made the diagram, you have written the assumption. The next point is you have to determine the velocity profile. Okay, so this is the third point. The next point is determine the non-zero velocity profile or component. So non-zero velocity component, in this case you have taken the Cartesian coordinate system. You may have the Vx, Vy, Vz. That may depend upon x, y, z as well as time in most general condition. But in this case, you have assumed that fluid is flowing in the z direction. This is the z direction. Fluid is flowing in the z direction only. So Vy and Vx are 0. And in x direction, in y direction, there is a no flow. You have the fluid flowing in the z direction. That is also the steady state. So time component will not be there. So, and y component, y is this direction. So in the y direction, you have the symmetry. So unless the end effects are dominant, you can assume that there is no effect of the y-axis. Okay, in the y-axis you have the symmetry, so you can remove also the effect of y-axis. Okay, now you have the Vz, which may depend upon x and z axis. Okay, now the fifth step, use the equation of continuity. So in the Cartesian coordinate system, it is very easy. dvx for the liquids, for the if the density is constant and steady state, you have the very easy equation for the equation of continuity. dvx by vx plus dvy by dy plus dvz by dz equal to 0. So this term will become 0. This term will become 0 because y is 0, x is 0, vy vx is 0. So when you solve this equation, dvz by dz equal to 0. When you solve this, you will get Vz equal to constant. So Vz is constant in respect to x, in respect to z. So Vz may not depend upon the z direction. Here, Vz may not depend upon z direction. So you have the Vz velocity, which is only depends upon the x direction. Okay, here you have the velocity which depends upon only x direction. This is the fifth step, use of the equation of continuity. Now the sixth step, you have to determine the non-zero shear stress component. The steps are same which we had used for the tube flow problem. Determine the non-zero shear stress component. Okay, so shear stress component tau is the second order tensor quantity. It has the 9 component. In the Cartesian coordinate system, you have the v tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, tau zz. These are the 9 component of the shear stress. Now the only component which is non-zero in the shear stress, which has the first indices representing the direction where velocity is changing. So first indices represent the direction where velocity is changing. And second indices represent the direction of the velocity. Okay, so first indices is x, second indices is z. Okay, the first indices where the velocity is changing in the x direction. So you have the tau xz, only the non-zero component, other all components are 0 or negligible. So non-zero shear stress component is tau zx, that we will use when the momentum balance, we will return the momentum balance. Okay, now seventh step, you have to draw the control volume for the momentum balance. So there are two rules. First, the geometry of the control volume should be similar to the geometry of the control volume should be similar to the geometry of the system. And second, the differential thickness of the control volume should be in the direction where you have the change in velocity. Okay, so this is the system flow on a inclined plate. So you have to make the similar type of control volume. Okay, so this is the control. Okay, so this point is z equal to 0. This point is z equal to L. This is the above this control volume is the part of the system. So basically the control volume is nothing but it is a part of the system like this. Okay, so this is the control volume. So in this control volume, the distance from the axis, z axis, that is this point. This point is x equal to present at x equal to x, and this point is present at x equal to x plus delta x. The thickness of the control volume, differential thickness is delta x. Okay, so this is the control volume. The length and width are same. Length is L, the width is W. That is given. Only the thickness will change. The original thickness of the system is delta. Here the thickness of the control volume is delta x. That is the lesser than delta. Now you have to write the momentum balance. Momentum balance on the control volume. Okay. So here we assume the viscous transport as a shear stress as a moment here we assume shear stress as a momentum flux. Okay, viscous momentum flux. So by assuming shear as a not friction force as a viscous momentum. Okay, now we will start the solution. So rate of momentum, the momentum balance equation is rate of accumulation of momentum equal to rate of accumulation of momentum that should be equal to rate of inflow of convective momentum minus rate of outflow of convective momentum plus rate of inflow of viscous momentum because viscous force is a momentum flux, not the friction force. Rate of inflow of viscous momentum minus rate of outflow of viscous momentum plus summation of all forces. So in this case, pressure is not a force because we are not applying any pressure drop. है ना? Here it is a freely falling liquid. So here we are not applying any pressure force. Here the force is only gravity. So summation of all forces. Okay, now you have to write the things. So because steady state, the rate of accumulation is 0. So first term, steady state, rate of accumulation equal to 0 due to the steady state. There is no accumulation of momentum in the system. When you have the steady state, there should not be any accumulation or any fall. Now second term, rate of inflow of convective momentum So convective momentum means momentum due to the flow of the fluid. And a convection means when the something is moving with the mass, that is called the convection. Okay. So convective momentum because of liquid is entering in the system. This is the open system. Liquid is entering in the system. Liquid is leaving from the system. So, so the force which is applied due to the entering of the fluid and the force which is removing due to the leaving of the fluid, that is called the convective momentum. Okay, so convective momentum enters with the fluid from this direction, convective momentum leaves from the controlled volume from this direction. So convective momentum enters from z equal to 0. What is the cross sectional area? That is delta x multiplied by w. W is the width of the control volume. So that is equal to delta x multiplied by w multiplied by rho Vz square at z equal to 0. Now third term, rate of inflow or rate of outflow of convective momentum. So convective momentum leaves from z equal to L. So z equal to L, that is equal to L W. This is W. W multiplied by delta x, that is the cross sectional area, multiplied by rho Vz square. Okay. So that is equal to delta x multiplied by W multiplied by rho Vz square from z equal to L. Okay. Now the fourth term, rate of inflow of viscous momentum. So viscous momentum, which is the viscous momentum? You have near you have it is shown that the non-zero shear stress component is tau xz. This is the non-zero shear stress component. Okay. Now the in the tau xz, the direction of the plane, or the direction where the stress is applied, that should be in the x direction, because it is the tau xz. So first indices represent the direction of the surface, second indices represent the direction of the force. And now the momentum, if it is a momentum, so it is in also the same, it is applied on the same surface, at this surface, that is the surface where the friction is applied, or the viscous momentum is applied. So when it is a tau zx, it will enters in the system like this. Okay, so viscous momentum always flows from high value to the low value. Okay, so the high value is at x equal to x, because at the upper surface you have the high velocity, you have the high momentum. At the lower surface you have the friction force, high friction force, because the solid surface, and at the lower you have the solid surface. This is the solid surface. So at the solid surface velocity is 0. At upper top layer you have the air, so the friction with air is very minimum, so you have the maximum velocity at the upper surface and lowest velocity at the bottom. So the momentum will flow from the top to bottom. Friction force or the shear momentum will flow from the top to bottom. So shear momentum will enter, tau xz will enter from the top surface at x equal to x, and the tau xz will leave from the system from the bottom surface at the x equal to x plus delta x. Okay, so you have to just substitute this value. So rate of inflow of viscous momentum surface, again surface area equal to this surface area, that is the L multiplied by W. This length is L, this width is W. So surface area, cross sectional area of the surface is L multiplied by W. So rate of inflow L multiplied by W multiplied by tau xz, shear stress at x equal to x. Rate of outflow, fifth term, rate of outflow of viscous momentum, that is equal to L multiplied by W multiplied by tau xz at x equal to x plus delta x. Okay, that is the rate of outflow of viscous momentum. Okay, now we have written all the momentum terms. The last term is sixth term, the forces, summation of all forces. So in this case only gravity will work in this problem, because we are not applying any pressure. Okay, and there is no centrifugal force. Okay, in this problem only gravity force will work, and gravity is a body force. So gravity is a body force, and gravity will always apply in the vertical direction. Okay, so actual gravity is applied in this direction. Okay, the angle of inclined surface is beta. Okay, so you have the beta component of the gravity in this direction, and because inclined, you have the surface which is inclined up to the with the beta angle from the vertical axis. So the beta, you have the beta component of the weight that will apply in the vertical direction. So gravity force acting on the fluid in z direction. That's why fluid is flowing, because gravity will force the fluid in the z direction, on the inclined surface in the z direction, acting on the fluid in z direction. So in z direction, you have the velocity profile volume. It is a body force. It will apply on for all on the volume. है ना? It is not a surface force. It is a body force. So L multiplied by W multiplied by delta x. This is the volume of the control volume multiplied by density. It will become the weight multiplied by gravity, and you have the cos beta. Beta component of cos beta component of the gravity. So this is the gravity force. This is only the force applied on the control volume. Okay. Now you have to just substitute all the values in the momentum balance equation. So all values in momentum balance equation. So for right hand side 0, rate of accumulation is 0. That is equal to viscous force. So what is the viscous force? Delta x w rho vz square at z equal to 0. Delta x multiplied by w multiplied by rho vz square at z equal to 0 minus delta x w rho vz square at z equal to L plus, then you have the L multiplied by W multiplied by tau xz at x equal to x minus, that is this term, and the rate of inflow of viscous momentum. Now you have the rate of outflow of viscous momentum, that is LW tau xz at x equal to x plus delta x. So minus LW tau xz at x equal to x plus delta x plus gravity force. Gravity is LW delta x multiplied by rho multiplied by g multiplied by cos beta. So this is your momentum balance equation. Okay, now in the momentum balance equation, the first two terms, this term and this term. In this term is at z equal to 0, this term at z equal to L. So width w is same, w is a constant that is not changing with z. The thickness, this is w. So w is constant. This thickness, width of the control volume is constant. So w is same. Delta x is also constant. The thickness of the control volume is constant at z equal to L and z equal to 0. Both are same. Okay. The next term is vz. Vz velocity is not depending upon z. And we have proved this. And we have proved by equation of continuity that vz may not depend upon z. So at z equal to 0 or z equal to L, vz will be same. That will not change. Okay. So in this equation, density is constant. That is the assumption that is our assumption. So these two terms should be equal. Delta x w rho vz square minus delta x w rho vz square, that should be equal. Okay. So first two terms are equal. And that's why should be cancelled out. Okay, so you can cancel these two terms, that is are equal and opposite with opposite sign. So the remaining terms are LW tau xz at x equal to x minus LW tau xz at x equal to x plus delta x plus rho LW delta x g cos beta equal to 0. Okay. Now you have to divide the next. You have done the momentum balance. You have written the momentum balance. That is the eighth step. Write the momentum balance equation for the control volume. Now, once you return the momentum balance equation, the ninth step is divide the momentum balance equation volume of the control volume. Okay, once you return the momentum balance equation, you have to divide the momentum balance equation by volume of control volume. So the volume of the control volume in this case is L multiplied by W multiplied by delta X. So you have to divide your equation to the LW delta X. Okay. So divide this equation. Suppose this is equation number 1. Divide the equation to the LW delta X. You will get tau xz at x equal to x minus tau xz at x equal to x plus delta x divide by delta x. Here LW delta x will be cancelled out, so you will get rho g cos beta, that is equal to 0. Okay. Now once you divide the volume to the control volume, you have to collapse the control volume to a point. So for collapsing the control volume to a point, you have to take the limit. Now take the limit. The differential thickness should be equal to 0. Delta x tends to 0. Okay, just write delta x tends to 0 in the equation. So limit delta x tends to 0, tau xz at x equal to x minus tau xz at x equal to x minus delta x divided by delta x plus rho g cos beta equal to 0. Okay. Now when you take delta x tends to 0, you will get the derivative. This equation will become the derivative, and derivative will always the final minus initial. Here you have the initial minus final, so you will end up with the negative side. So negative d tau xz divided by dx plus rho g cos beta equal to 0. Okay, this is your derivative equation. Okay, now once you return the derivative equation, you have to just solve it. Okay, so when you solve the derivative equation, you will get d, just rearranging this equation, d tau xz by dx equal to rho g cos beta okay. So here negative sign will be removed, so tau xz equal to this rho g cos beta, all are constant. Gravity is a constant value, rho density is constant in this case, beta is the angle which is constant. So when you integrate this, you will get rho g cos beta, these all are the constant, multiplied by x plus c1. C1 is integral constant. Okay, now before solving the now you can again, this is equation number 2. This is important equation. We have to return on this equation for the for the further solution. Now we can use the, now once you get this step, you will use the Newton's law of viscosity. Okay, once you get the value of tau, you have to use Newton's law of viscosity. Okay, so for the here shear stress is momentum flux. Yeah. So as momentum flux. So when you assume shear stress as a momentum flux, you have to take the negative sign. Minus mu dvx by dvz by dx. Okay, this is your tau xz. Okay, so just substitute the value of tau xz in equation number 2. You will get minus mu. What is the equation 2? This is the equation 2. Rho g cos beta x plus c1 and a tau xz. So just substitute the value of tau xz here. So you will get minus mu dvz by dx equal to rho g cos beta multiplied by x plus c1. Now mu is also constant, mu is a viscosity, that is also constant. You have to just rearrange the equation and solve it. Okay, so just I am rearranging the equation and solving the equation. So dvz by dx equal to minus x rho g cos beta plus minus c1 and when you integrate this, you will get Vz equal to minus x square, Vz equal to minus x square by 2 rho g cos beta minus c1x plus c2, where c2 is another integral constant. Okay, so you have this equation. This is equation number 3. I am again writing in the next page, so it will be easy. Vz equal to minus x square by 2 rho g cos beta plus minus c1x or xc1 plus c2. This is equation number 3. Okay, now you have to, once you get the velocity profile, you have to determine the value of the integral constant. So c1 and c2 are the integral constant. For that you have to put the boundary conditions. Okay, so boundary conditions in this case, so in the boundary conditions, we will use the either the velocity or we will use the interface. Okay, so in this case, at the interface, and the boundary condition in the momentum transport is, what are the boundary conditions? So So what are the basic boundary conditions in the momentum transport? The rules to select the boundary conditions. In momentum transport. So in momentum transport, first rule, first boundary condition, which is very obvious, that is the no slip boundary condition. So that tells you that at liquid solid interface or at fluid solid interface, liquid or that might be a gas. Okay, here in this subject we will solve only the liquid problem, but in momentum transport you may also solve the gaseous problem. At fluid solid interface, velocity of the fluid is equal to, is same as velocity of solid. That is the first boundary condition which you can use in the momentum transport. Second boundary condition generally defined as, if you have the symmetry inside a system, shear stress values are always known, that cannot be infinite, है ना? Shear stress values cannot be infinite. So this boundary condition is specifically used when you are solving the tube flow problem. And at the center, when you have the R equal to 0, the shear stress value should be finite. At R equal to 0, shear stress value cannot be infinite. Okay. The third type of boundary condition which we use in the momentum transport, if you have the two fluid interface, है so at two fluid interface, like in this problem you have the air and water. At the interface you have the air and water. Okay, at two fluid interface, the shear stress of both fluids should be equal. Shear stresses of both fluid should be equal. So these are the three different boundary conditions which you can use in the transport phenomena. Now come to this problem. In this problem, the first boundary condition, if you take the diagram, what are the boundary conditions which are used to solve to integrate the equation to the system? So in this system, there are two boundaries. One boundary is this, the lower boundary, which is a solid surface. At the upper, you have a air. And now above the fluid, that is the inclined surface, freely falling fluid. So you suppose there is a air, there should be air above the fluid. Okay. So here you have the air. This is the liquid layer. Then you have a solid boundary, solid surface on which the fluid is flowing. Okay, freely falling. Okay. So at air, so one boundary should be the air liquid interface, and second boundary should be the the liquid solid interface. And then you have to integrate the equation from this point to this point at x equal to 0 to the x equal to delta. Okay. So these are the two boundary conditions. So the boundary condition number 1, you can say at air liquid interface, the values of shear stress should be equal. This is the first boundary condition. That means at x equal to 0, tau xz for liquid should be equal to tau xz for air. Okay, that is the first boundary condition. Second boundary condition is, that is very obvious, no slip boundary condition. At no slip boundary condition at at x equal to delta, that is at x equal to delta, dz equal to 0 due to the no slip boundary condition. Solid liquid interface, you have the no slip boundary condition. Okay, now you have to use this boundary condition to determine the value of C1 and C2. So you have the two equations, because it is given in terms of, first boundary condition is given in terms of tau xz, so you can use the equation number 2 to determine the value of tau xz. Okay, so first we will use the first boundary condition. So boundary condition number 1, that is tau xz at air equal to tau xz for liquid. Okay, now we will, because air is also considered as a Newtonian fluid, air is a Newtonian fluid, so you can write mu air, viscosity of air multiplied by dvz by dx equal to mu liquid minus mu liquid multiplied by dvz by dx. These are the two equations. Okay, first, so you have used the Newton's law of viscosity. Now in this equation you can see that mu air and mu liquid. Okay, so mu liquid is, the viscosity of liquid is far dimensionally larger than the viscosity of air, or you can say the viscosity of air is negligible in comparison to the viscosity of liquid. So mu liquid is far greater than mu air. So this is all nearly negligible. Mu air in comparison to mu liquid, mu air is nearly negligible. So that is only possible. These two are constant. This value is nearly 0. The mu air value is nearly 0. So this is only possible, then dvz by dx should be very small. So that is only possible when dvz by dx is very small. or you can understand by the other terms. This is the one way to explain the boundary condition, or second way to explaining the boundary condition at tau at x equal to 0, tau air, tau xz air equal to tau xz fluid. What is the fluid? It might be or the liquid. So the friction in the air is very small, and the friction force in the air, viscosity of air is very small. That means the friction of the air is very small. And if you assume shear stress as a friction force, negligible. So if the friction of air is negligible, that means tau xz air, that is nearly equivalent to 0. That means tau xz is also, that's why tau xz liquid at x equal to 0 should also nearly 0. Okay, so because you are using the at the air liquid interface, because the viscosity, the friction force of air is 0, that's why tau xz is also 0. Or you can use this condition, dvz by dx is very small, that's why tau xz is also very small or negligible. Okay, so this both the arguments are correct. Okay, so finally you have the argument that tau xz at at x equal to 0 equal to 0. Now from equation number 2, you have to just substitute at x equal to 0. From you to substitute the value of this boundary condition in equation number 2. Now just substitute the equation, boundary condition equation number 2. You will get the equation number 2 is tau xz equal to x rho g cos beta plus c1. Okay, this is equation number 2. So in this equation, if x equal to 0, at x equal to 0, tau xz equal to 0, this is the boundary condition. So you will get c1 equal to 0. Okay, from this boundary condition, you will get c1 equal to 0. Now use the second boundary condition. That is at x equal to delta, Vz equal to 0. And to substitute this boundary condition in equation number 3. So when you substitute this boundary condition in equation number 3, where is the equation number 3? This is equation number 3. Vz equal to minus x square by 2 rho g cos beta minus c1 x c1. C1 is become 0. And c1 is become 0 plus c2. Okay. So you will get, first I am writing the equation number 3. Vz equal to minus x square by 2 rho g cos beta. Here mu will be there. Here you have mu also. So just correct it. You also have the mu at the denominator. mu multiplied by this is 2 minus C1 x by mu plus C2. Okay. Now in this equation, C1 is already 0, which you have written. Now you have to substitute the value boundary condition at x equal to delta, Vz equal to 0. So this will 0 at x equal to delta. So just substitute the boundary condition, you will get the value of C2, C2 equal to plus, in place of x, you will get the delta square by 2 mu rho g cos beta. Just substitute the value of C1 and C2 in equation number 3. This is equation number 3. Substitute the values of C1 and C2 in equation 3. You will get Vz equal to C1 is 0. Equation is minus x square by 2 mu rho g cos beta plus C2. C2 is plus delta square divided by 2 mu rho g cos beta. So take the common terms outside and take a bracket outside the bracket. So you will get rho g cos beta multiplied by delta square divided by 2 mu. These all terms will become the common. Inside the bracket you will get 1 minus x square divided by delta square. This is equation number 4, and this is your velocity profile. Okay, so your velocity profile is Vz, that is equal to rho g cos beta multiplied by delta square. These all are constant, divided by 2 mu in bracket 1 minus x square divided by delta square. This is your velocity profile. This is equation number 4. And when you substitute the value of C1, you will get the shear stress profile tau xz, that is equal to minus that is equal to rho g cos beta multiplied by x. This is equation number 5. So you have the velocity profile and shear stress profile. If you plot the velocity profile and shear stress profile, suppose this is your liquid flowing fluid. So I am plotting the velocity profile first. So velocity profile, if you have x equal to 0 is this point. This is the x equal to 0. This point is x equal to delta. Okay. So when you substitute the x equal to delta in this equation, in equation number 4, then this will become 1 and your equation will become 0. And the Vz equal to 0 at x equal to delta. And when you substitute x equal to 0, you will get this term, that is the maximum velocity. Okay. So you will get a parabolic velocity profile, this type. Okay. So this is the velocity profile. And this velocity profile is represented by the equation number 4. Okay, this is the basically the equation is like y equal to a multiplied by 1 minus x square by b. Yeah, this is the equation of parabola. Okay, now you have the shear stress profile. When you substitute x equal to 0, shear stress will become 0. When you substitute x equal to delta, shear stress will become rho g delta cos beta, that is the maximum value. Okay, so shear stress profile is like this. So shear stress is 0 at x equal to 0. Shear stress is maximum when you have the x, and it is a linear equation. Y equal to, this equation is like y equal to ax. Okay, so this is the equation of line. So this is your shear stress profile. Friction force profile. Friction force is zero at the air liquid interface. Friction force is maximum at the solid liquid interface. And meanwhile, in between, it will vary as a linear function of distance. Okay, so these are the profiles. Now you have to determine the maximum velocity that I already told you. At x equal to 0, you have the maximum velocity from equation number 4. Maximum velocity is that is at x equal to 0. So once you substitute the x equal to 0, you will get Vz equal to rho g delta square cos beta divided by 2 mu. This is the Vz max, maximum velocity. Okay. Now equation number 2 can be written as Vz equal to, this is a constant velocity, Vz equal to Vz max multiply by 1 minus x square by delta square. This is also equation number 4. Yeah. In this form. Now the last thing which you have to determine, that is the volumetric flow rate. Okay, so volumetric flow rate equal to surface integration of the linear velocity. So this is the linear velocity. This is the velocity of the fluid at that point, which is represented by equation number 4. So you have to integrate of the q equal to double integration Vz from where to where, from z x equal to 0 to x equal to delta dx, and from you have the y equal to 0 to y equal to w. Okay, so basically the volumetric flow velocity equal to here I am again making the diagram. So this is your liquid flowing. So you have the rectangular plate. Okay, so basically this is the rectangular plate. Okay, and thickness in this direction, thickness is w. Okay, so when the fluid is flowing in this direction, so the volumetric flow rate is this cross section area multiplied by linear velocity. So this cross section area equal to 0 to delta x integration multiplied by y. This is the y direction, y equal to 0 to y equal to w. Okay, so that will be your velocity. You know, if you check in this at this point, this is your plate. So the fluid which is flowing all over the surface, and the volumetric flow rate is this surface area multiplied by the linear velocity. Okay, just substitute the value of Vz. So y equal to 0 dx dy, y equal to 0 to y equal to w, x equal to 0 to x equal to w, x equal to delta, Vz equal to rho g delta square cos beta divided by 2 mu, in bracket you have 1 minus x square divided by delta square dx dy. Okay, once you integrate from 0 to the y, 0 to w dy, you will get only the w, because at y equal to 0 equation you will have the 0, at y equal to w, because the none of the quantities, all are the constant, x is not depend upon the y axis, delta is not depending upon the y axis, so you will get only the y, and y equal to w. So at outside you will get rho g delta square w cos beta divided by 2 mu. Now you have to integrate from the x equal to 0 to x equal to delta 1 minus x square divided by delta square dx. Okay, it is easy to integrate. So you will get Vz q equal to rho g delta square w cos beta divided by 2 mu. These are the constant quantities. Once you integrate the 1, you will get x, and when you integrate the x square, you will get the x cube by 3. So x cube divided by 3 delta square from x equal to 0 to x equal to delta. Once you substitute x equal to 0, both terms will be 0. Once you substitute x equal to delta, you will get q equal to rho g delta square w cos beta divided by 2 mu. This will become delta minus delta cube divided by delta square, that will also become delta by 3. So you will get q equal to 3 minus 1 2 by 3 rho g delta square w cos beta divided by 2 mu, or you can say 2 by 6 rho g delta square w cos beta divided by mu. So this is your volumetric flow rate. Okay, now once you know the volumetric flow rate, you can determine the average velocity. So average velocity equal to cross sectional area volumetric flow rate divided by cross sectional area. So V average. Okay, so V average you can calculate. V average velocity that is equal to V average volumetric flow rate divided by area. Area equal to area, cross sectional area of the flowing channel, that is equal to delta is the thickness multiplied by width, that is W, that is area, and Q you have written only Q equal to 2 by 6 or 1 by 3. 1 by 3, this is 1 by 3 है ना, इसको 1 by 3 कर लो. 1 by 3 rho g w delta square cos beta divided by mu. Okay, so just substitute the value, you will get 1 by 3 rho g w delta square cos beta divided by mu divided by area is delta w. So delta square है ना, that is okay. So when you divide this, you will get 1 by 3 rho g delta cos beta divided by mu. This is your average velocity. Okay, so you can written again here a equal to 1 by 3 rho g delta cos beta divided by mu. Mu is the viscosity, rho is density, g is the gravity, delta is the thickness of the film, beta is the angle of the inclined surface from the vertical axis. This is equation number 6. This is equation number 7. Okay, so after using the momentum balance, you have determined the velocity profile, you have determined the velocity, the shear stress profile, then you have calculated the volumetric flow rate and the average velocity. Okay, and you have also calculated the maximum velocity, and the maximum velocity is this. Okay, this is equation number 8. So so you have determined the everything, right? So this is the procedure will be the same. That this is the same procedure which you have used to solve the tube flow problem, right? You have to return the momentum balance equation. You have to collapse the equation and determine the velocity profile, and use the boundary condition. Solve the boundary condition. You will get the final answers. Okay. So the procedure will be the same. You have to just change the. You have to just change the geometry of the system, and based on the geometry you have to take the velocity, accurate velocity, non-zero velocity component. Then the procedure will be same. Okay. So any doubt in this problem?
सर
हाँ बोलो.
सर जो आपने एवरेज वेलोसिटी से पहले जो क्यू की वैल्यू यहाँ पे लिखी थी, इसमें डेल्टा क्यूब आना चाहिए था सर, क्योंकि हम स्टार्टिंग से डेल्टा स्क्वायर लेके चल रहे हैं, और जो हमने एक्स की जो यहाँ पे इंटीग्रेशन करके एक्स की वैल्यू रखी थी, उससे एक डेल्टा ऐड उसमें मल्टीप्लाई हो जाएगा.
That should be delta cube. That should be delta cube, and in the
then
last
average velocity into square add also delta.
yeah, here you will get the delta square. Okay, so you have understand the method. So we will solve one more problem, and then I will give the some few problem as a assignment, as a tutorial. Okay, so this is the simple method. Once you understand this method, you can design any part very easily. And once you understand this momentum balance method, you can design any fluid channel, a complex fluid channel very easily, because the procedure of the design is the same. The process design of the flow channel, that is the same. Even in the civil engineering, in the mechanical engineering, in the chemical engineering, in all the branches of engineering, in the fluid mechanics, the procedure will be the same. This procedure is only the procedure. Okay. But only the geometry will change, and you have to design the canals in the civil engineering, you have to design the hydraulic system in the automobiles, in the mechanical engineering, or you have to design the reactors in the chemical engineering. But the flow, the basic physics behind the flow is same. The momentum balance equations are same. Okay, so once you know that this system, you can design even the bearing system, and you can design the bearing of the equipment. You can design the hydraulic system for the automobiles or aviation industry. You can design the flow inside the canal for the civil engineer. And this is the design of the system. So this design, this is called the process design, where you can calculate the process parameter. So this design will be, the procedure will be the same, only the selection of the velocity profile and selection of the velocity components and selection of the drawing of the diagram, that will be changed. And the selection of the forces, what are the forces which apply. So in the civil engineering, there might be the shear forces might be the more dominant, and in the mechanical, the pressure force might be the more dominant, and when you use the hydraulic system. Okay, so that will only the change. Okay, so we will solve more problem in the next class.
All right, sir. Thank you, sir.
हाँ, और जो डिजाइन का जो एग्जाम था, तो I will also conduct one more quiz and 2 more tests, and best will be considered, है ना. So don't worry about the exams, है ना. Focus on learning more. Okay. So you
Excuse me,
all
sir.
get the good grades, and if you study, if you learn, you will get the good grades. Okay, so don't
Okay,
worry
sir.
about more about the grades, and just study and understand the things. Okay, okay. So we will meet in the next class.
Sir, I guess someone has query.
Sir, uh, sir, in the test that were given for transport phenomena, there was a question in the subjective test that to draw the direction of the shear tensors in Cartesian coordinate system. सर तो उसमें क्या करना था एग्जैक्टली मैं बता दीजिए.
Basically, you have to draw the surface, है ना? So suppose you have to write the direction of tau x z. So I have already told you that first indices represent the direction of surface and set the direction of surface, and second indices represent the direction of force. Okay, so this is the xyz coordinate system. Suppose this is the x-axis, this is the y-axis, this is the z-axis. So direction of surface is x. That means this is the x-directed surface. Okay, so in this surface, because the outer normal is in the x direction. Okay, this is the direction x-directed surface. Now you have to show the direction of the force. Okay, so direction of the force is z. So what is the direction of tau xz? Tau xz will be applied on this surface, and the direction of the tau xz will be this. Okay, on the x directed surface you have the force in the z direction, so this is the direction of tau xz. Similarly, if you have to make the direction of tau yx, okay, so y axis is this axis, so the plane in the y axis is the this axis, this is the plane in the y axis. Okay, this is the y directed plane, because y direction is this direction, outer normal in the y direction. Okay, in this plane, if your the direction of force is like this, then you have this is the direction of tau yx. So you have to
Excuse me, sir. One more thing.
हाँ बोलो.
Hello.
हाँ.
सर मैंने यही वाला क्वेश्चन सर इसमें 3D में बना दिया, पर लाइक सर मैंने इसमें प्रॉपर वो क्यूब के साथ बनाया, बट डायरेक्शन मार्क कर रखे हैं मैंने.
ठीक है ना? So basically the first indices represent the direction of surface, so you have to first make the direction. Outer normal is in the x direction, so of this surface, that is the direction of the surface, and the direction of force is z. The force is at the x directed surface, the force is applied in the z direction. If you have tau yx, so this is the surface of where you have the surface is in the y direction, the direction of the surface in the y direction, that is the outer normal direction of surface, and the force is applied in the x direction. So this is the x direction. This is the direction of tau yx. Okay, you can make on the 3D also, you can make on the cube also. And in the cubical direction, you can make cube and then you can show the direction also. Okay, so how many students have done this question correctly? Have you understand the question or not?
यस सर. सर एक्चुअली ये ना गलती से वेक्टर वाला वो कर दिया था मैंने, फिर मेरे को मतलब थोड़ा मैंने देखा, फिर इतने में मैंने सबमिट कर दिया.
कोई बात नहीं है ना, तो आई विल डू द रिलेटिव मार्किंग, है ना.
ओके सर.
थैंक यू सर.
ठीक है, so we will meet on the next class. ठीक है.
Okay, sir. Thank you so much, sir.